Here we go with Chapter 5 required homework solutions, starting with the questions. Question 2 asks if a car travels around a curve at a constant speed, and A, does its velocity change? And yes, velocity is a vector, therefore it has both a magnitude and a direction. And even if the magnitude isn't changing, but the direction changes, then yes, velocity does change. And therefore, if we have a change in velocity, part B, we also have an acceleration. So part A, the answer is yes, velocity does change because the direction changes. And part B, yes, there is an acceleration because if we have a change in velocity over time, then therefore we have an acceleration. Question 6 shows a picture of a ball on a string, and it's traveling in a circular path, like so, and at a certain point the string breaks. And it gives you a few options. It says maybe it continues following the curved path, maybe it goes straight out, maybe it flies off at some angle, and maybe it goes straight out. And as you recall from our in-class demo, the correct answer is it's going to continue going in a straight line path tangent to the circle because it has inertia. It wants to keep going. The only thing keeping it following that circular path was the string. That being said, question 7 asks also about that same ball on a string. It says before the string breaks, in question 6, is there a net force? And yes, there is a net force. We call that the centripetal force, Fc, and it asks what direction that's pointing in. And centripetal force is pointing towards the center of the circle. Question 24 asks if there is a net force acting on the planet Earth. And we know that Earth follows an orbit around the Sun, and since it's following an orbit, it's following a circular path, which means there must be a centripetal force. If it's orbiting like this, there must be some centripetal force keeping it in that orbit, and that centripetal force comes from the gravity from the Sun, the gravitational force between the Earth and the Sun. So, yes, there is a net force acting on the planet Earth. Question 26 asks if two masses are separated by a distance r, if we doubled the distance between them, then what would happen to the force? Now remember that force of gravity equals capital G times the mass of the two objects multiplied by each other divided by the distance between them squared. So if the distance goes up, if r goes up by a factor of 2 times 2, then the force of gravity is going to go down by, so force of gravity is going to end up going down because it's in the denominator. It's going to go down by a factor of 1 over r squared. So the difference is going to be doubled, the distance is going to be doubled, so the force of gravity is going to go down by a factor of 1/4, because it's 1 over 2 squared. In the first exercise, exercise 1, we have a ball traveling at a constant speed, v of 6 meters per second, and my son giving some commentary in the background. Say hi, Joey.
Hi.
And that ball is traveling around a circle with a radius of 0.8 meters. We're asked to find centripetal acceleration, and we know centripetal acceleration is v squared over r. So I take 6 squared divided by 0.8, 36 divided by 0.8 gives me a centripetal acceleration of 45 meters per second squared.
Okay.
That's good, thanks, buddy. Now, for exercise 3, we're given a constant speed. We have a different ball moving at a different speed, 3 meters per second. And we're given that it has a centripetal acceleration of 9 meters per second squared, and we're asked to find the radius of the circle. So, using the same equation, a sub c equals v squared divided by r, we're going to solve this for r. We multiply r up and divide by centripetal acceleration. We end up with an equation that looks like this. R equals v squared over centripetal acceleration. So we end up with v squared, which is 3 meters per second squared, divided by 9 meters per second squared. We end up with the radius, 9 over 9, which is 1 meter. In exercise 6, we have a car going around a curve. The mass of the car is given. The speed of the car is 20 meters per second, and the radius of the curve that it's going around is 40 meters. So we're asked to find centripetal acceleration first, and then we're asked to find centripetal force. Centripetal acceleration is v squared over r, which is 20 squared divided by 40, and we find the centripetal acceleration is 10 meters per second squared. Centripetal force, now there's two different ways you could do this. You could do mv squared over r, or simply mass times centripetal acceleration, m times a. And either way you do it, you get the same answer. You have 1,300 kilograms times 10 meters per second squared, which gives us 13,000 newtons. E10 has a person named Joe whose weight is 720 newtons.
Joe.
That's true. And it says that if his distance from the center of the Earth is doubled, so r is doubled, what happens to that weight? Now remember from the conceptual question earlier in this problem set, I think it was question number, let's see. Yeah, I know we talked about it. What question number was it? It was question number 26, where we increased the radius by 2. It's the same exact problem. If you recall, increasing the distance causes the force to go down by a factor of that change squared, because force of gravity is equal to capital G m1 m2 divided by r squared. G, m1, and m2 stay the same. The only thing changing is r, and that affects the force of gravity by a factor of that change squared. So since we're doubling the radius, the force of gravity is going to be reduced by a factor of 1/4. So we take 720 and reduce that by 1/4, or divide it by 4, and we get a new force of gravity equal to 180 newtons. And lastly, we have two masses, and we're trying to find the force of gravity between them. The force of gravity is equal to capital G, which is 6.67 times 10 to the negative 11th, multiplied by m1, which is 200, and m2, which is also 200, divided by the distance between them, which is 0.75 meters and squared. So you can plug in all of your numbers. Capital G is 6.67, m1 is 200, m2 is 200, and then r, which I actually wrote in here already, is 0.75, and I square that, and I end up with a gravitational force that is very small, because the force of gravity is actually pretty small for small masses, of 4.74 times 10 to the minus 6 newtons. All right, thank you. If you have any questions about any of those problems or their solutions, please send me an email.